Without any further ado, I would like to introduce Justin Kugler. All right, Justin Kugler is industrializing low Earth orbit and beyond. Justin has a wealth of knowledge in aerospace systems engineering, exploration, and defense systems from his experience with the intelligence community, NASA, and the ISS National Lab. He holds a BS in aerospace engineering from Texas A&M and a master's degree in mechanical engineering from Rice with a focus on aero-astronautics and intelligent systems. He's now Vice President of Advanced Programs and Concepts at Made in Space. Made in Space is leading the development of in-space manufacturing technologies ranging from the first 3D printers on the International Space Station to the revolutionary Archinaut System for fabricating functional space structures on orbit. Please, Justin.
Thank you. I appreciate y'all having me here today. You know, I've known Michael Lane for a number of years now, and I was really excited when he reached out and invited me to come talk with y'all today. So I'm gonna kind of give y'all a brief history of kind of who I am, where I've come from, and how that shapes my thinking and how we as a company approach, you know, the issue of space infrastructure and in-space manufacturing, and then walk you all through some of the things that we're working on right now, literally right now, to unlock that frontier. So as Layla said, I'm the Vice President of Advanced Programs and Concepts at Made in Space. That's a really fancy way of saying that I'm focused on new business development and strategic relationships to help grow the company across all of our functional sectors. I started my career in the intelligence community. I was a weapons analyst for the Central Intelligence Agency, starting back in 2003. But even before that, I was a NASA intern at Johnson Space Center. So I have kind of an interesting and roundabout way of going through the industry, in that I started as a civil servant, then went to grad school at Rice, and then came back to NASA as a contractor. And then I worked in the nonprofit world at the Center for the Advancement of Science and Space. And then I went into you know, the startup community when Andrew Rush recruited me to come work at Made in Space 5 years ago. And the reason why I wanted to kind of walk you through that history briefly is because I learned very early on in my career, and I know this is something that, you know, that Mike Mealing will appreciate, that delivering value to your customer, whether that is through a business transaction or, you know, whether you're, you know, civil servant, you know, performing your duty on behalf of the nation, delivering value to your customer is always top of mind. That is always the objective. And that's just as true as, you know, when I was on the president's analytics support staff, as it is, you know, when I'm, you know, writing a proposal for NASA to build, you know, the next generation in-space manufacturing system. Doesn't matter how good your technology is if you're not solving somebody's problem, if you're not delivering value. And I think that's something that, you know, we in the space community can do a much better job doing, is communicating how the work that we do is making people's lives better here on Earth. And that is a central focus of the work that we're doing at Made in Space. I would be remiss if I didn't mention that Made in Space is now a REDWIRE company. We were acquired this summer. REDWIRE Space is a new mid-tier firm that was created by aero-equity industrial ventures. This is very interesting for us because aero-equity is better known in the aviation sector. They've literally generated billions of dollars in value in taking companies that, you know, make parts for aviation OEMs, that make, you know, engine components and wing pieces, and they bring those companies together, help them, you know, raise their market cap and grow the industry. And in doing so, you know, they employ tens of thousands of people and have generated billions of dollars of value in the aviation sector. And they looked at, you know, what companies like Made in Space is doing. They looked at what our sibling business units at ROCOR and Deep Space Systems and ADCOL were doing, and realized that we could be stronger together than operating independently, and that by working together and combining the spaceflight heritage with the innovation and entrepreneurship that we all offer, we can put space to work for more people, for more customers, and generate more value. And so they created REDWIRE and invested in Made in Space because they believe in that vision, and they believe that it makes good business sense to do so, which has been a very exciting transformation for us. So when you think about REDWIRE as a whole, it not only includes the work that we're doing at Made in Space on on-orbit servicing, assembly, manufacturing, and low Earth orbit commercialization, it also includes the advanced sensors and components that companies like Deep Space Systems and ADCOL have been building for decades now. It includes their work on space domain awareness and resiliency. It includes work on digitally engineered spacecraft so that we can apply the same lessons learned for rapid R&D and rapid technology investment in the terrestrial sector to accelerating the technology refresh rate for satellite technology. And so you see that as we're putting all of these pieces together under the REDWIRE banner, we are rapidly accelerating our ability to generate full-scale mission solutions for a wide variety of customers across civil, defense, and commercial space, and to do so at scale. And as you can see, we're all over the country now. I'm in our corporate headquarters in Jacksonville, Florida, but we also bring to bear the experience of our technology team in California and our sister companies in Colorado, Massachusetts, and Maryland. Beyond that, we have a ton of experience, and even here at Made in Space. 2020 is actually the 10-year anniversary of Made in Space. I've been with the company for about 5 of those years now, and I met the founders actually back when I was working on the space station program. The guys at NanoRacks came up to me and they're like, "Justin, you were such a big help helping us get our first payloads on station. And we met these young guys just out of grad school. They want to put a 3D printer on the space station. Nobody's ever done that. Can you help them figure out how to do that the same way you helped us figure out how to put the nanolabs on the space station?" And again, that was my job. I was working in the ISS National Laboratory office at Johnson Space Center, and we were chartered by Congress to make the space station more accessible to non-NASA users and non-NASA utilization. And so our chief engineer, Mike Snyder, actually every so often likes to show around the pictures in 2011 when I was taking them on their first tour of Johnson Space Center and the space vehicle mock-up facility, and essentially showed them how we integrate payloads on board the space station. You fast forward to today, and we have a wide variety of manufacturing and operations payloads on board the space station. We are building satellites here in Jacksonville now, and we're expanding our work on what we call exploration, manufacturing, and exploration services, taking advantage of the fact that we now live in a policy environment where NASA and DoD as first customers are more amenable to commercial services and public-private partnerships. And without that forward-leaning approach to procurement, it would be a lot harder for a small company like ours to break into this market. And so I think it's important that we give credit where credit is due in our relationships with the government and opening up this sector. So Made in Space is my home. It's what I know and love, and so I'm going to talk more about Made in Space today than the other parts of REDWIRE, because I think that's most relevant to the discussion that we're trying to have here at Blue Marble Week about how we build space infrastructure and how we build the space economy for the future. And so even though, as I mentioned, we started with putting the first 3D printers on the space station, today, now that we're a company of almost 200 people, and most of them are here in Florida, it's more than just that. We've organized ourselves around what we consider our 3 main business verticals. The first is what we call satellite solutions. It includes in-space manufacturing and robotic assembly, but it also includes the work that we're doing on affordable, scalable satellite buses. Rather than targeting the small kind of throwaway end of the market, or going after the Maxars and Northrops of the world, who could bury us with in-kind contributions alone. We're focused on how do we create those core satellite capabilities that enable the affordable implementation of on-orbit servicing, assembly, and manufacturing, because there is an unmet need in that market for these kind of modular, adaptable systems, but don't cost what the Battlestar Galactica kind of missions of previous decades did. In parallel, we have a very robust portfolio of what we call commercial space products and services. It includes our pilot payloads that we're building in partnership with NASA to evaluate which industrial processes will lead to scalable products that can be manufactured on orbit and brought back down to the ground to be infused into terrestrial goods and services at higher value than their terrestrial competitors. It also includes advanced work that we're doing on on-orbit services. One of the coolest things I'm really excited about that we're working on right now is called Olaf. And I'm going to take credit for that name because it is a portable freezer that will hold minus 70 degrees Celsius for 4 days without external power. Nobody else has anything like that. And it's critical to NASA because they need that to bring down the backlog of biological and plant research science that's stuck on board the space station right now. But we've also found that there's tremendous interest in that capability in the terrestrial logistics market, as well as evidenced by the logistics challenges that companies are finding with transporting the coronavirus vaccines, especially to parts of the world that don't have the resources to implement large, heavy, constantly powered freezer storage. And then our third area where we kind of grew up from and where we still have a strong presence today is what we call space exploration solutions. And so that is work directly on making it easier, safer, and more sustainable for people to live and work in space. And just to show that this isn't just pretty artist pictures. This is all real work. Our Archinaut 1 program is funded through NASA Space Tech Mission Directorate Tipping Point program. We're working with DARPA on ESPA rings that can disassemble and reassemble themselves on orbit so that you can reuse that structure for satellite missions rather than throw it away after your primary and other secondaries are deployed. We're working with NASA Goddard on applying in-space manufacturing to enable large-scale optical interferometry from small sets, when before that would have been a $500 million mission. On the commercial space products and services side, you can see that we have a whole slew of new payloads either on the space station right now or getting ready to go up over the next couple of months. In fact, just last week, we completed the first successful on-orbit microgravity ceramic manufacturing demonstration. And that hardware and those samples are coming back down on the recent SpaceX cargo vehicle so that we can evaluate the process and lessons learned. And coming up just a few months later on SpaceX 23, we're sitting at both a crystal growth facility, not for biological crystals, but for industrial crystals, because you can still take advantage of that quiescent low gravity environment to grow optical materials that are of much higher quality and much higher uniformity than what you see on the ground. And as opposed to, my good friends that are working in biomanufacturing, we don't have to, take 10 years to get through, an FDA approval process to get our product out on the market. We also have a super alloy casting and heat treatment facility going up on SpaceX 23. And in all of these pilot payloads, we have partnered with terrestrial customers and terrestrial developers who have specific problems in material science that they can't solve with what they have on the shelf, and that they don't have a terrestrial alternative. And I think that's important when we talk about industrializing low Earth orbit and creating the new space economy, because what's hampered us in the past, because we've been trying to commercialize low Earth orbit, at least since the shuttle era, when I was a kid, back in the early 80s. And the problems that we've run into in the past are that there haven't been facilities that create material samples and product samples for which you can make a one-to-one comparison with the same thing on the ground. And that's what we're addressing these new facilities that we're building for the space station now. And then there wasn't any way to scale. So for example, protein crystal growth back in the 80s and 90s was what everybody thought the killer app for microgravity was going to be. But it turned out that you could, with advances in terrestrial technology, you could get to good enough on the ground. And it's really only been within the past few years that they've identified targets that for protein crystallography that can't be resolved on the ground, and that you still need to take to microgravity to grow. But even then, all that does is get you to the point of identifying what the structure of the protein is. There's still a whole slew of research ahead of that initial investigation to determine how you can create a product that benefits from that microgravity research. Whereas with these materials engineering focused facilities, once we get that proof of potential, we can go directly towards small scale batch production on board the ISS. And so that accelerates that product development curve, which I think is key to taking advantage of the lifetime that we have left on board the space station. And then as well, we're continuing to work on space exploration solutions. That includes our ongoing work on additive manufacturing on board the space station. We're working with NASA Marshall on a regolith printer that we'll be testing on the ISS later next year, as well as advanced work on hybrid metal additive and subtractive manufacturing, on orbit robotic welding. And we've also now begun work with Blue Origin supporting their HLS engineering work. So to focus a little bit more on our on-orbit servicing, assembly, and manufacturing portfolio, where we found that we can deliver the most value to start is helping add more value to small satellite missions. Traditionally, small sats have been constrained by how much functional payload you can pack into the small volumes that are available for small satellites. But if we can manufacture the apertures, manufacture and assemble the solar arrays on orbit without the constraints of the launch shroud, without the constraints of surviving launch, we can create much larger functional structures than what they would normally be able to carry by themselves. So for example, you can see in the picture labeled Halo, we were able to robotically assemble a 7-meter RF antenna where no human hands touched the structure. Even blown up to full resolution, it's really hard to see because it's so fine, but that also includes stringing the wire mesh onto that structure. That is a complete antenna right there in the picture. And we actually tested it by taking it up off on the roof of our building in Mountain View, California, and pointed it at a radio repeater on the other side of the bay in Oakland, and showed that it closed the link and raised the gain. Like I said, we're also working with NASA Goddard and DARPA's Tactical Technology Office on applying these technologies to enabling new classes of missions that previously cost hundreds of millions of dollars to execute. So for example, using extended structure manufacturing, we can deploy at high levels of precision outboard mirror units, so that you can do off of a ESPA class satellite better planetary science at a distance than what you can do with ground telescopes, with higher angular resolution than even Hubble and James Webb, because of the optical separation between the mirror units. The Eagle project with DARPA, we've partnered with Moog CSA to actually redesign the ESPA ring so that it can segment itself and be reconfigured into a backing structure. Otherwise, that mass is thrown away on most launches, and either deorbits or becomes orbital debris. But instead, by essentially making the ESPA ring so that it can unfurl itself after launch, you can carry more functional payload and increase your effective surface area on these small satellites. Whereas before, you'd have to pack all of your instruments to fit either on like one narrow facing side of the satellite. But our biggest project by far is what NASA now calls OSAM-2, short for On-Orbit Servicing, Assembly, and Manufacturing 2, which we lovingly call Archinaut 1. This is the first ever in-flight demonstration of robotic manufacturing and assembly. Off of this ESPA class satellite, we're going to use the same manufacturing system twice. First, it is going to extend a solar array wing out to a total length of 10 meters. Essentially, the principle is kind of like Venetian blinds in space. But in doing so, we can eliminate all of the complicated deployment mechanisms and motors that are traditionally required for a system like this. And then robotically, we're going to turn the manufacturing machine around and build out the other side a structural test article for NASA, so that they can evaluate the performance of the structure over time. This is important because it satisfies NASA's intent through the Tipping Point program, and that we are doing a functional demonstration of what an actual operational system might look like. And I would be remiss if I didn't mention that my colleagues at ROCOR are doing some amazing things with deployable technologies for small sats right now. But this is just the start of what we can do within space manufacturing and assembly, because the way you make a bigger structure with traditional deployables is you have to add hinge lines, you have to add geometric complexity. And so as the size of the structure, as the size of the object gets bigger, the cost increases geometrically with the complexity. Whereas with our in-space manufacturing system, you have that core manufacturing capability, but it doesn't get any bigger. All we have to do is add more feedstock. And so instead of getting that geometric increase in cost and complexity, we get more of a linear increase in cost and complexity. And that's why, for example, NASA's ISAT study group last year very strongly recommended that as we're looking ahead to the next generation of flagship space observatories, James Webb is about as big as you can go with traditional architectures. Just adding a small amount of increase to the diameter of that system, the cost increases with roughly with the cube of the diameter using these traditional approaches. So, nobody wants to spend 20 years and billions of dollars to deploy that capability. The taxpayers and Congress won't stand for it. But if we build these backing structures for these large apertures that the science requires on orbit, and then robotically integrate the fine surface features that are required to collect that science data and direct the light with enough precision so that we can get useful data out of it, that allows you to achieve the capabilities that the mission requires, but you don't have to break the bank to do it. So I'm going to show you all a little video of what the satellite will look like in flight. This was produced by our fantastic partners at Deep Space Systems. And so you can see that even after the manufacturing and assembly operations are complete, we have that residual robotic arm capability. And over the year that it spends on orbit, not only after manufacturing and assembly is complete, we're going to be testing that robot arm as well to see how it holds up over time, because this is a new modular low-cost design that we're developing in partnership with Motive Space Systems, because we can't have any one piece of the system be a significant cost driver. Before, when we were first starting on the Archinaut program 3 years ago, we went to some of the traditional robotic arm providers, and they wanted as much money for one arm as NASA was giving us to do the entire program. And so we realized that we had to solve some of those logistics problems ourselves in order to deliver an affordable, reliable, cost-effective system. And so that's the result of it today. But as cool as it is to see amazing concept art like that, this is the result of years of hard work. We started by demonstrating that core manufacturing technology in the thermal vacuum chamber at NASA Ames. And then we integrated it with a robotic assembly system and tested it in an even bigger thermal vacuum chamber with Northrop Grumman, where we showed that we could manufacture a simulated space structure and robotically integrate functional components onto that structure with no human in the loop. That was the key, to be able to show to NASA that we had developed this technology far enough to put it on a free-flying satellite. We had to show, in that ground test chamber, that we could do it without having to send our engineers and technicians in between every step to make it work the way it was supposed to. And so from those lessons learned, we're now working on that first flight scale system. And in fact, just a couple of weeks ago, we did vertical standoff testing out at Cecil Field we are now, I believe, up to the 10th generation of our extended structure additive manufacturing machine, and showed that we can produce those manufactured structures at the length scales that are required for the mission. And so we're now barreling on towards CDR, and we're on track to launch on a SpaceX rideshare mission in the first part of 2023. So now we get into the part that is really fun for me, and that's talking about why we want to do this. So, I'm an engineer at heart. I love solving problems. I love thinking about space, working on space. You can ask my parents. I've been obsessed with space for as long as I could communicate. I decided when I was 4 that I wanted to be an astronaut. And then when I was 7, I figured out that there are these people that build the things that go into space, and they're called aerospace engineers. And I decided when I was 7, I was going to be an aerospace engineer. And I've been fortunate enough to stick to that dream. but my experience, working in government and working outside of, the warm confines of NASA, where I'd been an intern, taught me that you have to deliver something. You have to solve somebody's problem. You have to make somebody's life better to get them to support you and what you're doing. And that is the laser focus of the work that we're doing at Made in Space. And so we're initially started with trying to make it easier, safer, and more sustainable for astronauts to go out on long duration missions, because it's literally not physically possible to carry every spare part and every tool you could ever possibly need, especially once we're talking about going back to the moon and on to Mars. We've also realized that we can take advantage of the unique microgravity environment of space to create new products and new services that make life better here on Earth. And that ranges from creating new national assets for overhead imagery, collections, weather and climate science that can't be matched by terrestrial satellites alone. For example, I was talking with a NOAA scientist a couple of weeks ago that they've always wanted to do microwave imaging and sounding from geostationary orbit, because that's what's needed to get to that all-weather, all-sky capability, so that you can look at the big picture, integrate all of the pieces, and then direct smaller assets in lower orbits to look at specific phenomena. But to do that from GEO and get that all-weather, all-sky capability, you have to have a really large aperture to be able to direct enough energy to get data with good resolution. And as a result, that's been prohibitively expensive. They've never been able to do it because of the costs. But with in-space manufacturing, we can build apertures that are large enough and affordable enough in GEO that you can take advantage of the miniaturization of radio frequency technology. We can take advantage of the ample amounts of solar power that are available at those altitudes, and even some of the new opportunities with disaggregation that are the result of work that the Air Force is doing on space-based solar power beaming, that it does become possible now to actually build that kind of large-scale, high-value space infrastructure for weather and climate science, for global telecommunications, and for other persistent platforms. We also think it's important because if we want to build a low Earth orbit economy that's sustainable, if we want to build permanent cislunar infrastructure, and we want to continue building on the work that's been started with James Webb, we've got to learn how to put space to work for us, rather than fighting the environment, fighting to figure out how to survive inside of a launch shroud. If we industrialize space and we take advantage of space itself as the build volume, rather than making everything fit origami style, we can do that, and we can solve all of those problems. And it's important that we continue those investments, because if we don't, we already know for sure that other people are. Just this year, on a automated mission, China launched their first 3D printer and 3D printed CubeSat deployer. You can see pictures of what they did on the automated capsule here on the slide. And rather than just try to replicate what we've already done on board the space station, they decided to try something different. They printed with carbon fiber reinforced polymer composites. So they didn't just copy the Made in Space printer, though there have been previous news reports where they said that they were going to build the Made in Space printer on the Chinese space station. They've instead looked at how can they build something that can compete with our capability, because it's public information that we can print with engineering thermopolymer on board the space station. It's public information that NASA has been investing in hybrid metal manufacturing capabilities. So they decided to do something different, but that also shows that they can build capability to match ours. And if you look at reports over the past several years, they've made it clear that it is their strategy to build large structures in space, that their program is focused on long-term wealth creation, and that they have also assessed that in-space manufacturing is required to maintain space command and control. And I think if we look at the coming century, this is a question of whose values will be predominant in the space environment. And do we want it to be an issue of a command and control style philosophy, or do we want to build a marketplace where everybody can come who wants to come, and everybody who wants to work to solve problems can solve problems, and we can all make each other's lives better, and we can all build a better economic system, but do so in a way that doesn't sacrifice individual liberty. And this isn't just my idea. If you look at the recent reports that the Secure World Foundation and AIAA produced for the Biden administration, they say the same thing. They believe that it is critical that the government play an early role in advancing space-related technologies to commercially relevant levels of maturity, and that we need to accelerate the use of government-sponsored demonstration missions to get us past the TRL Valley of Death and show that these things work, and give our procurement officials the freedom that they need to achieve national goals in space through these revolutionary technologies. When we have that effective alignment of policy, programs, and partnerships, we can make it work. We've seen that with commercial cargo. We're seeing that happen with commercial crew. And we very strongly believe at Made in Space on REDWIRE that on-orbit servicing, assembly, and manufacturing is the next leg of that triad, where we can take advantage of private investment, government first use, and an effective policy framework that allows entrepreneurship to thrive, to create these new capabilities and new services, and bring us forward into that next generation, so that we can get to a fantastic future like we show here, where we have giant comms arrays in space, where we can build space structures and habitats that are large enough to support hundreds, if not thousands, of people living and working in space, and unlock the potential of the solar system for science, for exploration, and for our economic advancement.
Justin, that was amazing. Thank you very much. I'm sorry, I was kind of caught off guard because I was looking at that image. Can you post that last image for a second longer? Because
sure.
I was just kind of imagining what that future looks like, right? So Monday and Tuesday, we're really focused on rocketry and infrastructure and workforce development. Tuesday, we started talking about hardware, gas stations in space, space tugs, things like that. I really made a pretty strong rule about no CGI, right? This isn't Elon Musk with his CGI'd Martian settlements. It's not Jeff Bezos and his CGI'd herd of elk orbiting the Earth on a O'Neill cylinder. This is hardware. This conversation, the meetings that we're having yesterday, the day before, and today, it's about hardware. Now, today we're definitely talking about aspirational stuff, things that are moving to possibly out to the moon, right? And we are talking about the nearer term future, 2020, 2020 to 2035 is the max.
Hmm.
But I love seeing this array of stuff you've already got, right? You showed us a lot of hardware, stuff you've already accomplished. And then if this is built and that is built and that is built, it enables these
All of
things
this.
as an obvious logical extension. I'm pretty sure you know Michael Mealing, but his integrated space plan, I wish it had this clarity of detail, right? That would be helpful to all of us. Because this is a plan that has, pardon the expression, this is a plan that has legs, right? It's based on heritage. It's based on, this is where we are right now, actually, not hand waving, but actually. And then if these things happen, then it enables this next piece. So thank you. This is exactly what I was looking for. I appreciate that. I didn't mean to go on a rant on my own. This is your Q&A. I just wanted to share my enthusiasm. I think we could spend the entire 20 minutes talking about how you named a freezer Olaf, but we're not going to do that. So thank you for that. That was really great. We do have some other interesting questions. I want to point out that some of the folks on our call here have some pretty big corporations. Oh, perhaps they left. No, they didn't leave. There's a fairly large engineering group from Italy here, so I think they might be interested. We're going to ask for you to put your contact information in here later, into the chat. And I believe there is a representative from the Aerospace Futures Alliance. You showed that REDWIRE map of where your locations are. Certainly that's a big stretch from where you were when you were just made in space. But the Aerospace Futures Alliance, I'm sure, would be happy to pull some of your resources up here into the Washington State, Seattle region. So
Well, there's more to come.
Expect that.
We're not done with our acquisition round.
Good. Good to hear that. Do you want to share anything about that, or is that is that close to the vest?
That's definitely close to the vest. I can say that we're likely to have some announcements soon on that front, but we're definitely not stopping just yet.
So let's talk about the growth, right? I mean, that's kind of what we're talking about here. Yeah, I first met Jason and his buddies. They were straight out. I first met them when they were at Singularity University. That is the official founding of this, right? Mm-hmm. Those guys, 2 or 3 guys at Singularity University. That was 10 years ago. Yeah. Is that right? 10? Okay. So not the REDWIRE component, because I know that is even larger, but just the Made in Space crew. How big are y'all now, total personnel?
I think as of right now, we're about 150.
150. And you joined when they were 5 years old, so half their age. What employee number are you? I'm pretty sure I know the answer, but I want you to tell people the answer.
So I was the 22nd employee when I was hired. And as of now, by seniority, I think my seniority number is number 9.
Good for you. Nice job. I asked the same question of Nagar Faher yesterday. You were working at NASA. You had a good gig with CASIS. That's the International Space Station's National Lab. I don't know how to describe it, but it's the group that brings people to the International Space Station. So you had a good gig there. It was a big risk. I don't even think Andrew was on board as CEO yet, right?
He was. He
was. Okay.
All right. For not quite a year when he hired.
Okay. All right. So Andrew had been there for Andrew Rush is the CEO of Made in Space. So he'd been there a year. What made you jump from the very steady paycheck with, a wife, a mortgage, and a kid, and what made you decide, oh, hey, I want to go build something crazy in space?
So the work that I had been doing at CASIS was focused on building the industrial R&D portfolio for the space station. So I was out there, getting, the Goodyears and Dow Chemicals of the world to start thinking about using, the ISS as a research platform, the same way that they work with, say, Sandia or Argonne or, other terrestrial national labs. And it occurred to me that there was so much potential for what we could do with entrepreneurship and industrial development and product development on board the space station. But I didn't feel like that was really being taken advantage of with the focus on the ISS as a science platform. And I had tried to help bootstrap some entrepreneurs into getting their work on board the space station. And some of them literally only just flew their experiments for the first time last year. And so I decided that I could take everything that I had learned and be more effective at pushing the industry and creating this vision that we have for the industrialization of low Earth orbit, working in industry for an entrepreneurial organization that I could staying in the nonprofit world. And Andrew heard that I was thinking about making a change and cornered me at ISPCS in 2015 and convinced me that, and I was actually thinking I was being recruited actually to go to NASA headquarters. And I was weighing, do I want to be more on the policy side, writing reports for what people should be doing, or do I want to jump in feet first and actually do it? And Andrew convinced me that I needed to come work for him and actually do it.
It's hard to say no to Andrew, for sure.
Yes.
Side point, I like this event that we're having, but boy, I miss those those conference meetings where you could just get together and hang out and get to know somebody really well. So, all right. So you've got this roadmap. You've got a greatly increased team. You've got new resources in REDWIRE. Is there something, we're talking about building out infrastructure, and we're trying to couch it between the next few years. You've got some missions that are coming out in the near term, 2022, 2023, 2025. One of the professors from Cal Poly in the question in the chat's talking about, we're building the U.S. interstate system, right? We are creating the roads with the pieces, with the off ramps connecting, one town to another town to another town. I think that's a pretty good analogy. Certainly something we can talk to Congress about. Where in this interstate map, if you will, is made in space? Like what role? Like we talked about gas stations yesterday. We talked about Ubering to space on the first flights. We talked about taxiing when you need to go from point A to point B. So if we're going to really stretch this cars, roads, freeways analogy, what role is made in space?
The analogy that I like is one that actually a colleague of ours gave to us, and it was in the context of a project that he was working on, but he kind of sees us as the general contractors of space. You know,
Okay.
we not only supply the infrastructure, but we then use that infrastructure to build the functional things that other people use to generate value. Whether we're talking about building communications arrays that are much larger and much lighter than what you can build on the ground, or whether we're talking about building the factories that'll produce industrial crystals and Z-band fiber and things like that. I've been kind of like making the joke that we're the BASF of space,
All right.
in that we figured out how to use space itself, the intrinsic value of microgravity, to make things better and to deliver more value. And as we continue to integrate into REDWIRE, and you see REDWIRE space continue to grow and evolve, I think that is going to be become more of a focus on integrated solutions and services, where we'll provide the backbone, and then maybe we'll partner with like an instrument provider or an electronics provider, and then maybe like a prime that has the back end and already has that relationship with that trusted relationship with the customer, where we're kind of the glue that brings all of those disparate pieces together, and does so in a way that makes it affordable and scalable for the customer.
Terrific. One of the big arguments for why we're having this meeting, the Blue Marble Week, in the first place, and the whole series, is to talk about space as infrastructure, right? We talked about workforce, we talked about capabilities and technology capabilities. What does your workforce look like? Who are you looking for? What do you need? Where are the skills gaps that are missing? Because my hunch is if you grow to 200 people that fast, you're missing some stuff.
No, that's a great question. So at the REDWIRE level, we're trying very hard to not drown ourselves in overhead, and so they're trying to keep the actual REDWIRE management team as light and nimble as we can. And so I'm very fortunate to have the mentorship and leadership on the business development side from Al Tadros, who is our new chief growth officer, who's been with REDWIRE a couple of months now, and who the folks that are on this call that might know him probably know him from his decades of service at Maxar and SSL. But he came over here for the same reason that I did, because he believes that this is the future, and that REDWIRE as a whole, kind of with Made in Space leading the way, can deliver these capabilities in a transformational way. And but from the workforce side, we need more systems engineers. We need people that can look at that big picture and figure out, okay, this is what needs to be done, and then direct the subject matter experts and the vendors to creatively create these solutions and solve these problems. Because most of the work that we do is firm fixed price. We don't traditionally do cost plus contracting. Sometimes we'll stretch and do time and materials, where that makes more sense for the customer. But we believe very strongly in doing what we say we're going to do, and doing it at the cost that we quoted. And so I think having that most of the hiring that we're doing right now is in systems engineering and spacecraft engineering, because we want people that can creatively do integrated problem solving. We don't want people that are just going to hit the same nail with the same hammer over and over again.
Later today, we're going to have Tom Olson come in and talk about the difference between risk space and safe space. We've decided that we don't like the words new space and old space. They don't really have any value anymore. So taking on projects that are risky is, I think, kind of the new definition. I'm going to ask a somewhat sensitive question. Feel free to decline. We only have just a few minutes before we move on. Can you talk about the gross amount of contracts that you had under management that justified the REDWIRE acquisition? It was a pretty big acquisition, right?
So the exact details I'm not at liberty to discuss.
Right.
But I can say that our backlog was significant enough that we were the largest of the acquisitions.
Okay. So I know that y'all had at least, and this is me speaking, not you speaking, there were a couple contracts, multi-10s, multi-50s, and a few, I think there was one $110 million contract. That's all public record.
So our Archinaut is our largest program, and that is a matter of public record, and that is a $74 million NASA contract.
Okay, so that was your backlog, that was your pipeline of contracts, and that certainly justifies a pretty healthy multiple, and I'll just leave it at that. Certainly, I'd like to know what that multiple is, but we'll gently, gracefully move on to our next speaker. Thank you so much, Justin.
Excellent. Thank you so much. We appreciate it.